All right, so today we're going to learn about something called an electron configuration. So an electron configuration really is just a bunch of letters and symbols that describe where the electrons are in their orbitals. So think of it as sort of like the address for the electrons within an atom. It's analogous to in the Bohr-Rutherford diagram when you would draw the orbits and place a certain number of electrons within those orbits. But of course, we know that this is not a correct model for an atom and where the electrons are located. And so what we're going to be learning in this lesson today is, well, if the Bohr model really isn't accurate, how do we describe the location of these electrons within an atom? And so why do we care about any of this? Well, of course, the location of those electrons in 3 dimensions is within an atom is really important because it helps us, gives us an indication about what types of bonds are likely to occur. But we will be getting to that a little bit later. So we're going to start with the simplest element, which is hydrogen. And without a periodic table, I think most of us know that we can predict the number of electrons that it will have. It has 1 electron. And so if we're talking about ground state elements and their configurations, which is where we're going to start, then we know that that 1 electron is going to have a principal quantum number of 1 because it will fill that first energy level. And if that's the case, when we know the allowed values for our secondary quantum number are 0 all the way up to n-1. And so that should make sense to you that the L value, the secondary quantum number, will be 0. Okay, so remember that describes an s orbital. And so now I have all of the information that I need right now to write out the electron configuration in an appropriate format for hydrogen. And so this is how it works. So knowing this information above, I'm going to begin filling that s orbital. So I would write the element symbol here to the left. And then I know that I'm talking about the first shell or the first energy level. So that's where this first 1 comes from. And then I indicate the orbital by the letter designation, so the type of subshell. And then as a superscript, or in the exponent if you like, I'm going to indicate the number of electrons that are in that subshell. So in short form, the electron configuration for hydrogen would be 1s1. So the Aufbau principle, I mean, I think this will make a lot of sense to you. It's called the building up principle. In fact, I think it translates to that directly. It states that electrons are filled from their lowest energy orbital to the highest. And this shouldn't come as a big surprise. This is nothing really new. Even when we were working with the Bohr-Rutherford diagrams in grades 9, 10, and 11, this is how we filled our electrons from the inside out, right? Lowest energy level to the highest. So this is nothing really new. So sometimes, alternatively, instead of the electron configuration, you might also see something called an orbital diagram that might be used to present basically the same information in just slightly more detail. So I'm going to show you 2 different ways that you might see that information depicted. So you'll either see some sort of a square, sometimes even a circle, with the element name to the left. And then what you'll see drawn are the electrons. So electrons are drawn either as an arrow or like a half arrow. So if I was drawing this like this for hydrogen, it would have an electron that would look like that. Sometimes, to make it quick, you'll only see it drawn with like half of the arrowhead sort of thing, right? Now, other times what you'll see instead is just a sort of a line drawn with the electron in it. So if I were drawing it this second way for ease, there it would go. Now below there you'll also see the orbital designation. So for instance, if this electron I know to be in the 1s, you would see below there just like a 1 and then the s. And then same over here. So that is what we call an orbital diagram. And you can imagine that these get quite large as we start looking at larger atoms with a greater number of electrons. So you'll remember from our last conversation when we looked at hydrogen, and specifically we looked at the spin of electrons. We saw that, you know, the spin of those electrons can either be positive or negative, clockwise or counterclockwise. And so by knowing that and knowing that no two electrons can have the same four sets of quantum numbers, we deduced that you could have a maximum of 2 electrons per orbital. And that's going to become important. How we designate that in orbital diagrams. So just imagine here's our square where we're going to indicate where our 2 electrons are. If I have 2 electrons, let's say for instance in the 1s orbital, then I'm going to demonstrate that they have different spins by showing them as spinning in the opposite direction. So I would have one right side up arrow and another one in the opposite direction. And what that designates is the fact that those 2 electrons are in the same orbital, but they have 2 different spins, one clockwise, one counterclockwise. So let's apply that to helium. So you'll remember that helium has 2 electrons in total. And so if we know that, then we can easily write out its electron configuration. So helium. And I know that it has that 2 electrons, but they're both in the 1s orbital. So here's my 1s showing the orbital designation. And since there are 2 electrons in that s orbital, and that's the maximum number it can hold, I'm going to write a little 2 here. So there's my electron configuration. If I were to draw the orbital diagram, I'm going to show, and I'm just going to use a line just to save space here. And I would write 1s underneath to indicate that it is in fact the 1s orbital. I'm going to show the fact that it has those 2 electrons, but that they have opposite spins. So one with a positive spin and the other one with a negative spin. And that's it. Now in the past with our Bohr-Rutherford diagrams, we would have known that after the first energy level comes the second energy level. But now with these subshells, it makes things a little bit more complicated. And we will come up with a system to know the order of filling these subshells. But for now, I'm just going to tell you, and we'll get there eventually. After the first subshell is filled with 2 electrons, the next lowest energy orbital happens to be the 2s. And that's not maybe a big surprise, but here we are. So when I go about trying to draw the electron configuration for an element like lithium, which has more than 2 electrons, it has 3 electrons, I know where to put that 3rd electron. And it's going to go in the 2s. So let's give this a go. So lithium. And I know that it has, remember again, I'm just going to write that it has 3 electrons in total here. And where the heck am I getting that from? Well, I'm getting it from the periodic table and the atomic number. So lithium, I know its first electrons are going to fill that 1s orbital. And remember, the s orbital can hold a max of 2 electrons. So 1s2. But so now instead of having 2 electrons, I only have 1 left because I've used up 2 of them. The extra electron is going to go in that 2s. So I'm going to draw right next to it 2s. And since there's only, and so the 2 is indicating it's the second energy level, the s is indicating the type of orbital, and I've used up 2 of the electrons, the extra one goes right here. There I go. So I'm done. The orbital diagram, you'll see a few different kind of permutations of this. I like to show it where the energy levels are indicated too in the diagram, although sometimes you'll just see you won't see that indicated in the diagram. So I know that the 1s orbital is of lower energy than the 2s. So I'm going to show the 2s as being sort of slightly elevated compared to it, but in the same sort of vertical column. So I'm going to try to squish this in here. I've used up way more space than I intended to, but anyways, here we go. 2s. And so now I can start to fill up those electrons. Right, so here's 1, 2, and then my 3rd one's going to go up here. And some people will say, well, does it matter if it's positive or negative? It has a positive spin or negative spin? Not really at this point. But there will come a point where the spin will matter. And when we get there, I will bring it up. Now, just to highlight, just to explain what I mean by these maybe not being shown in terms of energy levels, sometimes what you might see is you might instead see them all sort of in a line, in a horizontal line. So just know what you're looking at. So just to see if you're on the right track, what I'd like you to do is I'd like you to try to do the electron configuration and orbital diagram for beryllium. So pause the video, give those a go, and then resume when you're ready to check your answer. All right, so knowing that beryllium on the periodic table has 4 electrons, I'm going to fill those from lowest to highest orbital, energy orbital, so beryllium. And so I know that I'm going to fill the 1s shell with 2 electrons, and that will give me 2 left over. And so the next orbital to be filled is the 2s, so I'm going to 2s, and it's going to get 2 electrons as well. Now, as for the orbital diagram, let's take a look at that. So if I'm drawing them in those sort of vertical columns, I'm going to draw my 1s right here, and then my 2s right below, or right above rather. And I'm going to start filling my electrons. 1, 2, 3, 4. So now all of those electrons, all the 4 electrons have been accounted for. Hope you did okay with that. So now is where things get a little bit more complicated. So you may remember that there were 3 different types of p orbitals because of their orientation in 3 space. So we have the px, the py, and the pz, right? So really each of those can hold 2 electrons in total. So if we know the px orbital can hold 2 electrons, the py orbital can hold 2 electrons, and the pz can hold 2 electrons, then in the p subshell in its entirety, we know that there are 6 electrons that can be held in total in the p orbitals. So let's just keep that in mind. So 6 electrons in total in the p subshell because of the px, the py, the pz. We're going to need to keep that in mind as we move forward. And so if I were asking you to write the electron configuration and orbital diagrams for boron, if we look on the periodic table, we know that we're looking at an atom that has 5 electrons, right? So let's just see how that works itself out. So 5 electrons in total for boron. So boron, we know that we're going to fill the 1s orbital with 2 electrons. We're going to fill the 2s orbital with 2 electrons. And so now we're going to fill the 2p. And so we know that the maximum number in the p subshell is 6, but in this case we only have 1 electron in there. So we're done. As for the orbital diagram, this is where we start to see things get a little messy. So I would have my 1s, speaking of messy, and then I would have my 2s just above it. And because it's not an s orbital that gets filled next, but a p, we're going to put it in its own sort of column and with an energy slightly above. And remember, we have the px, the py, and the pz. And you can write in 2px, 2py, or 2pz to demonstrate that these each have their own orientation. Or you can simply just put 2p underneath a set of 3 lines or squares, whichever you prefer. And then fill accordingly. So here's my 1, 2, 3, 4, and then my 5th. Now, it doesn't really matter which of these you've put in. Just put it in the first one. That's typically what you'll see. And now what we're going to do is we're going to talk about, well, what happens if there are more than just a single electron in that p subshell? What the heck? How do we organize that? Well, so then this is where Hunds Rule comes in. Hunds Rule states that when electrons are added to orbitals of equal energy, so like what we just saw with the 2px, the 2py, and the 2pz, a single electron will enter each orbital before a second one enters any one orbital. Okay, so that's the first part. So what we're saying here really is this. We're saying that, let's say, for instance, I had 2 electrons filling this p subshell. What I wouldn't want to do is to put 2 of them in the same subshell before filling the others. This would be incorrect. So I don't want to do that. No. So alternatively, what I would do is I would have 1 in this first shell and then the second one here. And so I would fill each of these 3 orbitals, the px, the py, the pz, before I would start to double up in any single orbital. Now, another thing that I should mention is that the spin of each of these has to be parallel. In other words, it has to be in the same direction. So, for instance, here, 1, 2, 3. Right, so let's say, for instance, I had 3 electrons in my p subshell. I would need to have them all spinning in the same direction. So given this information, what I'd like you to do is I'd like you to take a couple of minutes and I'd like you to draw out the electron configurations and the orbital diagrams for nitrogen, oxygen, and fluorine. Pause the video, work that out, and then check in with me. All right, and so if I'm drawing out the electron configuration for nitrogen, I remember that it has 7 electrons. So the electron configuration is going to be 1s2, 2s2, 2p3. And so if I just picked this orbital diagram sort of prefabricated online, and so just to make our lives easier, so I'm going to take the 7 electrons that nitrogen does have and fill them. So 1, 2, 3, 4, and now is where I need to remember Hunds rule. I've got 3 electrons, but I'm not going to double up until I have put at least 1 electron in each of these 2p orbitals. And notice that I've made sure that the spin is parallel. Hopefully you did okay with that. So now as I'm adding electrons moving across a period, all I'm really doing is, every time I'm just adding an extra electron. So instead of, for oxygen, instead of it being 2p3, it'll be just 2p4. And all I would do, I shouldn't really have erased this, but anyways, all I need to do is to just kind of keep the same orbital diagram as I did for nitrogen, but then now that I have a single electron in each of my 2p orbitals, I can go back, and I'm just going to make this red for emphasis. I can go back and I can double up on one of my p orbitals, but in having that electron has to have the opposite spin. And I'm not going to go through the misery of describing what the fluorine orbital would be, but we would see an extra electron here and an extra electron here in my p orbital. And so one might think that the order of filling subshells is just sort of in order, going through the shells and then going through the subshells in order. But and it kind of appears that way at the beginning, 1s and then 2s and then 2p and then 3s and then 3p. But lo and behold, take a look at what happens when we compare the energies of the 4s with this should actually be 3d. Let me just fix that. Arg. So this should be 3d. And so if we look at that critically, it appears that the 4s actually has lower energy than the 3d orbital. And so that means that we need to start filling the 4s orbital before we fill the 3d. Which is sort of counterintuitive. And there are other examples of that as we move up energy levels. Let me show you this in a different way. So if we were looking at an orbital diagram written in terms of energy, again, see, just looking at the format, you can see the S's are all in the same column, the P's are all in the same column, the D's in the same column, and I'm going to get back to this actually, and then the F's are in their own column. So notice that there are some weirdnesses here, like the fact that the D's have 5 orbitals, and that makes sense because we have 5 different configurations, each with 2 electrons. So that means that a D orbital, a D subshell can hold a maximum of 10 electrons. And the F, remember, has 7 different orientations, and therefore at 2 electrons per orbital can hold a max of 14 electrons. So this is an example just to kind of show you how things can get a little bit crazy and convoluted with the orbital diagrams. So for larger atoms, I won't likely ask you to draw the orbital diagram, except maybe for the valence shell. But back to the weirdnesses, you'll notice that the 4s has lower energy than the 3d, and the 5s is lower energy than the 4d, and the 6s has lower energy than the 5d, and then the 4f is lower than the 5d, and so on and so forth. So it does get kind of crazy. So we need to have some sort of a system to remember the order of filling these subshells, and so here it comes. So I am going to show you a handy dandy trick with the periodic table that will help you to know the order of the subshells, and it's pretty amazing actually once you sort of clue into the way that the periodic table is arranged. But if you don't happen to have a periodic table, then this is a quick trick. So notice what I've done is I've written 1s and all the s subshells in the same column, and then I've gone over and written the 2p and then 3p, 3d, all the allowable subshells for the given energy levels. And so you'll see lots of it'll probably be neater than mine, but you'll see lots of diagrams of this online. So what you do is you start sort of down here where the 1s is, and you draw almost like a line through it. So I'm going to go 1s, and then I come back down here and I go through here at 2s. So we know that we fill the 1s first, oopsies, then the 2s. Then I'm going to go back here, back down around 2p, 3s. And then I come back down, 2p, 4s. So notice that I passed through the 4s before I went back to the 3d, 4p. And instead of going to the 4d, I'm going to the 5s. And that sort of continues. Ugh, I wish it wasn't doing this. And then on and on and on. I'm going to do that again just to show it a little bit more neatly. So there you can see just a little bit of more of a neater presentation. So until we figure out how to use the periodic table to help us with this, this diagram will help us to know the order of filling those subshells. So let's do some practice. So keeping this diagram in the frame, just so we can remember the order of filling the subshells, if I were to ask you for the electron configuration for sodium, well, I would look on my periodic table and I would identify how many electrons it has. So take a minute to do that. And so I know that sodium has 11 electrons. And so I need to house those electrons in the appropriate orbitals. Let's do that. So those 11 electrons, so I'm going to put some in the 1s2. I'll work out the subscripts or superscripts later. 2s2. So far I've used up 4 electrons. 2p. And so let me see. So I've got 2, 4, and then so I'm going to go 2p6 and then I've got 1 electron left. So 1s, 2s2, 2p6. Now I'm going to fill the 3s. So 3s. And I'm going to put 1 electron in there. So let's just fix this up. And then I can go ahead and count my electrons to make sure I've used up only 11, which is what sodium has in the ground state and in its atomic form. 2, 4, And then plus 6 gives me 10, and then 11. I'm good to go. All right, now I'd like you to give this a try with calcium. So pause the video, give this a whirl on your own, and then let's see how you do. All right, so check your answer. I'm just going to read it out so it might make it easier. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. For calcium's 20 electrons. All right, give these last two a try on your own and we'll take it up together. A couple of things I want to remind you of. In these, you're going to get into the d orbital. So remember, there are 5 different orientations for the d orbitals, which mean at 2 electrons each, a total of 10 electrons. And remember the f orbitals, there are 7 orientations with 2 orbitals each, which means that there will be a total of 14 electrons allowed in an f subshell. Here's a diagram just to remind you of that. So pause the video, give these two a whirl, and we'll check in a second. All right, so let's check in to see how you did with this. So you'll notice the front end of things tends to be the same. But when we look at the back end, what I want you to pay attention to is this little bit here. So we get to the 3p6, then back to the 4s2, and then the 3d5. So hopefully you got that okay, just remembering the order of the subshells. And so lead follows along like this. I'm going to read it out, and you can check as you go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then we go back down to 3d10, 4p6, 5s2, then down to 4d10, then over to 5p6, then down to 6s2, and now we jump to 4f14, and then the 5d10, and then the 6p2. So if you didn't get the answer, check in with one of your classmates to have them explain why that is the correct answer, and I will always go over this tomorrow with you if need be. So if you're like me, then you found that pretty tedious to have to go back and look at your chart every time and whatever. So I find that to be kind of painful. So what I'm going to do is now I'm going to teach you a quick trick using the periodic table to help you work through electron configurations. Some people still prefer the other method, but I find that using the periodic table is quick and efficient as long as I remember a couple of details. So before we do this, I want to draw a relationship between the periodic table and its structure and the number of electrons in each subshell in total. So we know that in the S subshell, of course, there's only one orientation, so there's 2 electrons allowed there. The P subshell, well, we have the PX, the PY, and the PZ for a total of 6 electrons. And in the D subshell, we have 5 orientations and 2 electrons each, so that gives us 10 electrons. And in the F subshell, 7 orientations at 2 electrons each gives us a total of 14. Let me try to draw this, 14 electrons total. So now let's keep that in mind when we look at the periodic table next. So let's take a look at the periodic table here. Well, when I look at the columns here, remember helium would be over here, and we know that when we filled our orbitals up that it's 2 electrons, both 1 and the 1s. So for all intents and purposes, what we're going to do is we're going to think about helium as being over here, right here, instead of over here. And so when I look at this, there's in this block right here, I'm going to just sort of highlight it. In this block right here, we have 2 columns. In this block over here, we have 1, 2, 3, 4, 5, 6 columns. All right, so we have 6 columns here. Remember, we had 2 columns here. I'm going to use a different color now. Over here, when I look at this block, let's count over and see how many columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh. Are you seeing any kind of trend? So hopefully without even having to count, you know what to expect in this bottom little section with the lanthanides and the actinides. Yes, you're right. There are 14 columns. Not 17, 14. And so with good reason. So remember, of course, helium really should be placed over here in this section. And so we name different sections of the periodic table based on how many columns they have, and that helps us know what orbitals are being filled if the element ends up being in that block. So this portion of the periodic table, the S block, here's our D block, here's our P block, and here's our F block. So we're going to use that in order to quickly do an electron configuration. Let me show you. So for example, let's just say I was talking about chlorine. So we know that chlorine is right in here. In fact, let me see if I can write that out. So I'll write that out right in its spot. Chlorine, Cl. I guess it's having a little bit of trouble writing over this document. Anyways, we know it's there. There, it's at least being marked. So I would go, well, 1s2, or sorry, 1s2, counting in helium here, 2s12, 2p6, 3s2, and now here's 3p, 1, 2, 3, 4, 5, 3p5. So just by counting blocks along the periodic table, I can come up with the electron configuration. Let's take a look at manganese. So manganese, I think I want to say was 1, 2, 3, 4, 5, was right about here. So there we go, there's manganese. So if I know, here's my first energy level, second energy level, and so on and so forth as I go down. There's one little trick when I hit the D block and the F blocks. And so that's the only kind of trick to this. So I'm going to show you what happens. So, here's my 1s2, 2s2, 2p6. I'm going all the way across to get to manganese. 3s2, 3p6, 4s2. Now, if you remember the chart with the arrows through it telling us the order of the subshells, you'll remember that after the 4s2, I start to fill the 3d. So when I go from the S block to the D block, I have to reduce the energy level by 1. So instead, goes 4s2, and now I'm in the 3d block, 3d1, 2, 3, 4, 5, 3d5. And that's how I would finish off, counting over to manganese. Now let's say, so if this is my 4s, that means this is my 3d row. This is my 5s, that means I begin the 4d right here. If this is my 6s, then this would be the 5d. Now you'll remember also that, this little part, the F block kind of squeezes in right in here. And so just to save space, we write the F block separate, but really it sort of fits in right here in the periodic table. And so I need to remember to go from my 6s down to this F block before beginning my D block. So this is my 6s, but however, this is my 4f. I can't write that out really well. 4f, and then I go back to 5d. So my F block is 2 lower than the energy level of my S block. So again, 6s2, 4f14, 5d, and then I go back here to 6p. So if I were doing lead, which you'll remember was over here, okay, I would go through and say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Now I need to remember to go down here. 4f14, 5d10, and then back to 6p2. All right, so that's where we're going to stop for today. I'm going to see if you can draw out the electron configurations for another example and then assign some homework for you to try, and then we'll pick up where we left off during our next class. So for tomorrow's class, I'd like you to try drawing out the electron configuration of palladium PD, and we'll check in tomorrow and do a couple of warm-ups.